Mm-hmm. Sure. Okay. Do you have the problems in front of you? I don't have them with me. No, I'll just take them. Okay, so this is particle kinematics. We going? Number 10. An object moves according to the acceleration function. A of t is equal to 2 cosine of 4t. We did? Okay. Well, I don't think it should. Let's do one part of it. Change directions. We did talk about this, yeah. Okay, so you're given that the velocity at time 0 is positive 1. So we have to integrate the acceleration to get the velocity. So velocity as a function of time is equal to 1/2 sine of 4t plus some constant. And we know that if you plug in time equals 0, you get 1. So 1 is equal to 1/2 sine of 0 plus c. So c is equal to 1. And then it asks you questions. There's at what time does the object change directions? So to see when it changes directions, you have to find when the velocity is equal to 0. That would never happen in this case. Times t?
Yeah, but it's like v equals a t. It's not a constant acceleration.
Oh, yeah, that's right. So you can't use the constant acceleration equations here. Okay, because, right, this, if you have this function that's not a constant, then those don't apply. Yes? So look for when it switches concavity. Yeah, you could do that. You mean to find when it changes directions? The first part is at what time, and it gives a range, does the object change directions? And that's going to happen when, or the only candidates for that are when the velocity is equal to 0. We find the velocity function set equal to 0. In this case, it never happens. And then it asks something else. What's the object's position at the time it changes directions? It never changes directions. This question is stupid. Who wrote this question? They're fired. No, this is the one I'm doing up here. The displacement vector is the position at the later time minus the position at the earlier time. Mm-hmm. And it works the same way in 1D, except they're just not vectors. So yeah, 2D question. Henry, did you have a question on 2D kinematics? Yeah, sure. Okay, who has the problems? Oh, okay. Oh, that's a lot like the one we did.
Maybe a different one.
Yeah, that's true. We just picked 6 at random, Nick. How about number 2 with the helicopter? Okay, so a helicopter is, this is how you draw a helicopter. And it's moving at an angle of 15 degrees above the horizontal with a speed of 20 meters per second. And an object is dropped from a height of 55 meters. And then there's a bunch of questions. What's the velocity vector of the object the instant it's dropped? Drop instant. How long will it take the object to hit the ground? And then in that time that the object is falling, how much higher will the helicopter get? Yes, that's right. So at this one, yeah, we'll figure out the velocity vector of the helicopter, and then that's going to be the initial velocity of the object. How much higher does the helicopter get while the object falls? So the velocity vector is going to be 20 times cosine of 15, 20 times sine of 15. Could someone punch that in? I don't know that. Three O. Okay, so that's the velocity vector of the helicopter. The helicopter keeps doing that. And the object just has that velocity at the instant it's released. And then it accelerates down at 9.81 after that. What does the path of this object look like after it's dropped? you may ask yourself. Yep.
Parabola that opens down, but it's going to start a little before.
Yep, that's exactly right. So it's going to, even though this object is just dropped from the helicopter, its path is going to look something like that because it's starting with a vertical component of velocity. You know what I mean? And the second question, how long will it take the object to hit the ground? So let's put so if this is the helicopter, let's put the origin on the ground beneath the helicopter when the object's dropped, beneath the object at time equals 0. And so then we can figure out what variables we know and want. Looking for t. We know the acceleration. Do we know the initial position? Yeah, 55 is the y position, positive 55. X is 0. Do we know the final position? Right, we don't know the x component of the position, but we do know the y component. We know the initial velocity, we just figured that out. We don't know anything about the final velocity, so this is what we have to work with. So is there a single equation that'll let us solve for t? I think this should work. Py is equal to P0y plus V0y t plus 1/2 AY t squared. So 0 is equal to 55 plus 5.18 times t minus 4.905 t squared. That's 1/2 of 9.81. You can use the quadratic formula. Anybody have or remember what that is? Yeah? 3.91, and then there was also a -1. But that's the one that we know we never use. So that's the elapsed time. Did you have another question? Okay. And then C, how much higher does the helicopter get in that time? Okay, so now you have to be careful because the object is in free fall. Its acceleration is down at 9.81, but the helicopter, we're hoping for its sake, is not in free fall, right? The helicopter has a constant velocity of 19.31, 5.18. And if velocity is constant, then the acceleration is 0. And so we can use this same approach we did before. Think about what we know, what we want. we're looking for the y position at time t. We know the acceleration is 0. We know the elapsed time. We know the initial position. We know the initial velocity. And so it looks like we can use the same equation again. Py is equal to P0y plus V0y t plus 1/2 ay t squared. So Py is equal to 55 plus 5.18 times 3.91. And then the y component of the acceleration is 0, so this all goes away. And you get 20 or something. Is that right? Can someone calculate that? So you get like, well, you get like 75, I think, 75.81. I think that number sticks in my head. Okay, so 75.81 meters. Okay, so has the helicopter gone up 75.81 meters? No, that's the final height. And so the y component of the displacement, is that what it is? So 75.8.
Should be, yeah, 75.25.
So 75.25 minus 55, because that's the thing's height at the instant it's dropped. And so you get an answer of 20.25 meters. That's how much higher the helicopter is at the time the object hits the ground. Any questions about that? Okay. This is this. This yours, Jill?
Yeah.
Okay, so the next thing we have to talk about in 2D kinematics is relative motion. Relative motion is a lot more useful in 2 dimensions than in 1 dimension. Who remembers what relative motion is? True. Yes, it's that one, and we had the equations where we used that little memory trick of the fraction multiplication. Remember? Okay. In 1D motion, this said position of, I'm going to call it P relative to G. Now the P and G can be anything, but I'm going to do this because it almost always is ground in these problems, is equal to the position of P relative to something else, I'll call it A, plus the position of A relative to G. Who wants to guess how this changes in 2 dimensions, this equation? Yeah, exactly, they get vector hats, that's perfect. So it works exactly the same, it's just now that those are vectors instead of, yes? Well, yes, so it would work the individual components if you have some x's and some y's, or you can this says we're including both of them at the same time. But you can always break it up into one x equation and one y equation. That can be anything, but I put it like that because almost always the ground. So you're always, in almost every problem, you're going to have some measurement or calculation assuming that it's fixed to the ground, and then some measurement assuming it's fixed to something else, a truck or a spaceship or an alien or whatever. And A is for alien. It's almost always an alien, so that's an A. No, I'm sorry, I don't have them. I'll give those back on Wednesday. Okay, so what do you think happens if you take time derivatives of everything in that equation? It still has to hold, right? It does. So what do you think you get? Yes. So you get the relative motion equation for velocity. And do it again and you get acceleration. And, you know, we've already done problems thinking about it this way, but let's do a couple of example problems. Okay, so let's say that you have a launcher that can shoot a ball up at 4 meters per second. And now you put it on a cart, and the cart is rolling 3 meters per second to the right while you launch an object up into the air. How far horizontally will the ball be from the launch point when it lands? No, 0.2 meters.
So first we just have to find how long it's going to take to straight up and then plug that time into how long it would take for a cart to move 3 meters per second.
That would work, yeah, but I'm going to do this as using the relative motion equation to figure out an initial velocity vector. But the way you're thinking about it would give you the same answer. Okay, so the initial velocity what we want is the velocity relative to the ground. So the velocity of the ball relative to the ground is equal to the velocity of the ball relative to the launcher plus the velocity of the launcher relative to the ground. So this is the ground, this is the launcher. We want this one. So velocity of ball relative to the ground is equal to, what's the velocity vector of the ball relative to the launcher? 0.4, yep. So that's the one that's 4 meters per second up. If you had a camera, so if the launcher had a GoPro on it, at the instant the ball's launched, the GoPro would just show it going straight up, okay? Because the GoPro is also moving with the cart. So this is 0, 4. And then what's the velocity of the launcher relative to the ground? 3, 0, yep. And so the initial velocity is 3, 4. And now we can just use the two-dimensional kinematic equations. I'll put the coordinate system on the ground right below where the ball's launched from. Okay, what do we want to find? We want to find px, okay? We don't know time. We know acceleration. We now know the initial velocity. Well, let's do positions first. So the initial position, we know something about the final position. We know the y component because it's going to be on the ground. We know the initial velocity. We just calculated that. We don't know anything about the final velocity. So is there an equation that works with these? What? I think it turns out that there's no equation that works here. Right. And so what we want to do instead is set this aside and calculate t and see if that helps us. Okay, so this is just an intermediate variable. It's not, we would have been happy if we didn't have to get time, but yeah. So we'll go py is equal to p0y plus v0y t plus 1/2 ay t squared. So 0 is equal to 0.2 plus 4t minus 4.905 t squared. Quadratic formula says, so we get a negative answer, and we get 0.863 seconds. Yeah, even you can program your calculators to do the quadratic formula too if you have a graphing calculator. So come ask me about it sometime and I'll put it in there for you. I can do it in 30 seconds if you don't mind that it only does real roots. Yeah. Have you guys done complex? Oh, yeah. Okay. That's what I was talking about, not fake ones, but I like that idea. Yes. Yeah, I can do it even faster if you don't mind that all the roots are fake. Okay, yeah. You could do it that way. So in that sense, maybe, I mean, this is the way that I thought of doing it. I said, well, what we're given will give us enough information that we can figure out the initial velocity of the ball. So I was just going to find the initial velocity of the ball. And I did that by using the relative motion equation. Then we break it back up into components, yeah. But if you did it that way on a test, that'd be perfectly fine, you know. This is the way it sort of occurred to me more naturally. Okay, so we take the positive time, and now we can plug that time. So now that we know t, that's over here in our known, and now we can use the equation that says px is equal to p0x plus v0xt plus 1/2 ax t squared. So px is equal to 0 plus 3 times 0.863 plus 0. And so px is equal to 2.59 meters.
So theoretically, if the cart like kept going after the thing was launched with the ball, I'm assuming like the machine the ball would land back inside the tube.
Yes. But that would only work if there was very little air resistance on the ball. Yeah, if you did that with a pinball, it would probably work. You know, sort of a heavy, a dense thing like that.
Well, and you also exactly.
Yep.
But what they're really good in that
I think this would work. I think we could make this work in lab. Let's try to do it on Friday. Remind me. I bet we can make it work.
You can find a launcher for us.
We have launchers, and they're nice and straight. You can get it so it's shooting straight up. I'll bet we can make that work. Oh yeah, those launchers are great. They make a lot of noise. That's sort of a plus. Okay, let's do another one. So let's say that there's a river. And it's moving 5 meters per second. And it's 50 meters across. And let's say that a swimmer aims 60 degrees from the shore like this. So this is 60 degrees. And let's say that the swimmer can swim 2 meters per second. Where on the opposite shore will the swimmer end up? Yes. Yep. So the swimmer just keeps on doing this thing, and the water here. So you can think of like the swimmer keeps doing this in the water that the swimmer is in at that instant, and that water is moving downstream. He'll eventually get there. He might die, but if he doesn't die, he will get there. Yeah. 50 meters. Yeah. We got wider. You know, the Mississippi goes through the Twin Cities. Okay. I don't know how worldly you guys are.
Well, Landon thought that Duluth was in Chicago. Chicago was a state. So,
No, he didn't.
yeah, he did last year.
Okay. Yes, very good.
Yeah, not in Chicago.
Okay, so what are we going to do here? How are we going to solve this?
We're gonna try our best.
That's good. Yeah, right. So we're going to say, so we want to figure out the velocity of the swimmer. Everything here is constant velocity. So the velocity of the swimmer relative to the ground is equal to the velocity of the swimmer relative to the water plus the velocity of the water relative to the ground. The velocity of the water relative to the ground, what's that? Yeah, that's the current. So, and if we do a coordinate system like this, then that's in the positive x direction. And what's the velocity of the swimmer relative to the water? Yeah, and we have to be a little careful with that angle, but that's the right idea. So here's the coordinate system. And we want, right, yep. So the velocity of the swimmer relative to the water is 2 times cosine of 120, 2 times sine of 120. And so that is 1, negative, and then positive 1.732. And then the velocity of the water relative to the ground is 50. So the velocity of the swimmer relative to the ground is equal to negative 1.732 plus 50. You want to? Okay. So for 1.732, I have the perfect problem. Okay, but that's the velocity. And this is all these velocities are constant. There was no acceleration given. So, so now let's put the coordinate system. I put it, okay, so here's the swimmer getting ready to jump in from above. I'm going to put the coordinate system at the swimmer's starting point. All those things stay the same because the orientation stays the same. So now let's think about what we know, what we want. The acceleration vector is 0 because the velocities are constant. We don't know the time. We know the initial position. We know something about the final position. What's that? Yeah, so we know Py is equal to positive 50. We're trying to find Px, that's right. Yeah, we can find time. So I think that's how we're going to have to do it. And then the velocities, we know that the initial velocity is what we just calculated. Final velocity we'll leave out. And so yeah, is there an equation that works for these? No. So we'll solve for time, and then we'll know the time, and then we can solve for px. So I think this is the same pair of equations we used before. P y is equal to P0y plus V0yt plus the accelerations are all 0, so that goes away. So 50 is equal to 0 plus 1.732 t. So t is equal to
28. Wait. Yeah,
28.87.
Yep. How many decimal places
That's
do
fast.
you want us to?
That's a fast swimmer.
How many decimal places do you want us to round to?
I really don't care, but it's probably a good idea to pay attention to significant figures and just stay in the habit. But I do too. I just always ignore it.
Only one?
Here's what I think you should do. I guess since 50 is really only one, then your answer would be 30. Yeah, don't do that. That's ridiculous. I don't know. I don't care. You should use however many significant figures you want, but you should, in the back of your mind, feel bad about being sloppy. Okay, so now that we have the time, we're going to use px is equal to p0x plus v0x times time plus no acceleration part. So px is equal to 0 plus, what was the x component? Positive 4 times 28.87. And what do you get for that?
115.47.
115.47. So a long way away. Yeah, that's not so far to walk. He'll be okay. Could you figure out what angle he would have to swim to land exactly across the shore? Yeah, you would just, so the way you would do that is you would just set your final position to be 50 in y, 0 in x, and then, oh yeah, that's a good point. The rivers, yeah, even if you, yeah. You're right, that would be it. Yes. Yeah, you're right. So the fastest you can get across is just swim straight across and then just do the extra walking. Let's take a 10-minute break, and at 10 minutes to 9 or so, I'll give you a problem to work on together. Okay, let's shut up now. And everybody listen to me now. Yes. Okay, so here's the problem I want you to work on. Have you ever heard of the vomit comet? Have we talked about that? They use it to train astronauts for zero gravity. What?
Is it the plane that they like dive so it creates a zero gravity?
Yeah. Okay, so here's what we're going to do. So let's say that this plane goes, 200 meters per second. Okay. And let's say that in a coordinate system with the y-axis up and the x-axis horizontal, it starts out with a velocity vector of so what did I say, 200 meters per second? So 200 times cosine of 20 degrees, sine of 20 degrees. Okay, so first, calculate the position versus time function. Calculate the position as a function of time. With that velocity, that initial velocity. So that the acceleration is 0, negative 9.81. That's really sort of unrelated to that's just sort of an exercise in those kind of calculations. Then use relative motion to determine the acceleration of objects in free fall as seen by observers on the plane. On this plane. So the idea of this is that we're going to have an acceleration on this plane that makes it so that to somebody on that plane, if you drop something, it looks like there's no acceleration. That's why it's simulating a weightless. Yep. Someone inside the plane drops it, and it looks like it doesn't accelerate. Yes. It looks like it just stays there. It really is in free fall. And that's what it feels like to you, too, because you're in free fall just tumbling around. Well, it does it gradually, I think they definitely warn you as that's about to. Yeah. Yes. Yep.
Do we have to determine the x component of the acceleration?
Yeah, we're going to do it all as vectors. But the x component is going to stay the same. Yes. But just do the whole vector calculation. Okay. Good. Okay, so part A, that was sort of a dumb question. I thought it was going to, I don't know. I just made it up on the spot, and it turned out to be kind of. But the way that part A works, you know that this is constant acceleration. And so you know that position of x as a function of time is going to be in this form. And you know that the y position as a function of time is going to be in this form. And then you can just fill in what you know. This really doesn't matter. You can put the origin of your coordinate system wherever you want. We'll just assume those are 0. And so this is equal to 200 times the cosine of 15. That was 187.94. The x acceleration is 0. And then the y component, you have 68.40 times time minus 4.905 t squared. Okay, so if you write this as a vector, the position as a function of time is 187.94 t, 68.4 t minus 4.905 t squared. Yeah. Okay, so this is, so if you knew that your plane at time equals 0 had that one velocity vector, this is the path that the pilot of the plane has to take. Okay? Yes. Okay, so that's what the pilot does. And so now we know that the acceleration of the plane relative to the ground is equal to 0, negative 9.81. That was sort of the starting point of this calculation, but you can also take two derivatives again and get that. Okay. And now we want to know, so now we're imagining that there's an object on this plane that's dropped. And so if you drop something and there's not much air resistance on it, and there wouldn't be much air resistance on something you drop inside the plane because the air of the plane is moving with the thing. Even though it's moving really fast, it's not exposed to that fast-moving air. You know that the acceleration of the object relative to the ground is 0, negative 9.81. So now the relative motion equation would say the acceleration of the object relative to the ground is equal to the acceleration of the object relative to the plane plus the acceleration of the plane relative to the ground. So 0, negative 9.81 is equal to acceleration of the object relative to the plane plus 0, negative 9.81. And so the acceleration of the object relative to the plane is 0, negative 9.81 minus 0, negative 9.81. So 0, 0. Any questions about that? Yes. So the idea of the first part is, so the plane is not at a constant velocity. The plane is accelerating as if it was in free fall. That's what we want the plane to do. So this position function, that's what the plane has to do in time in order to go through a parabolic arc that keeps a constant acceleration downwards of 9.81. Okay. So the plane, yeah, the plane just goes through a parabola. It basically, the plane has a starting velocity and then it just is in free fall. And you might think like, well, that plane doesn't even need an engine, you know? Well, it does if it's going to land safely, but it could just go through free fall, except there's a ton of air resistance on planes, you know? And so if this plane really just turned off its engine at that velocity, it would do something very different than this parabolic arc. And so it needs the engine in order to make it simulate free fall. But now that the plane simulates free fall, something that's really in free fall inside the plane has the exact same acceleration as the plane. And the relative motion equation says to someone in there, you drop it and it just hovers there because the relative motion equations are what tell you that. Any other questions about that? Okay, so how about a car accelerates backwards at 50 meters per second squared. As a cup of coffee is dropped. Yeah. Well, no, you know, this is, and this actually, so this is big acceleration. So this is like what would happen if a car hit something, you know? So, right, big deceleration. Yep. Because it's moving forward and accelerating backwards, so it's slowing down. Yeah, probably not that bad, but you're thinking of velocities, but these are accelerations. Well, we don't know. It depends how quickly they. So for something stopping from 50 miles per hour to have an acceleration of 50 meters per second, it would have to stop over a time of 1 second, which is a huge amount of time. You know what I mean? So, yeah, or like it's a very big pillow or something. So that wouldn't be so bad. But I don't know. I think probably if you were going 10 or 20 miles, maybe even 10 miles an hour, and you hit like a wall or something else going the same velocity the other direction, you'd get an acceleration like that probably. So this cup of coffee is dropped. The observed acceleration of the coffee cup inside the car. Okay, well, we know that the acceleration of the car relative to the ground is 0, negative 100. We know that the acceleration of it all starts with C's. So this is the car. This is the acceleration of the cup relative to the ground. If it's dropped, it's just in free fall. So this is 0, negative 9.81. And I did my vector wrong on this. I did it wrong. negative 100x 0y. Right. And so now the relative motion equation says acceleration of the cup relative to the ground is equal to the acceleration of the cup relative to the car plus the acceleration of the car relative to the ground. And so we have 0, negative 9.81 is equal to acceleration of the cup relative to the car plus negative 100, 0. And so the acceleration of the cup relative to the car is equal to 0, negative 9.81 minus negative 100, 0. So that's equal to positive 100, negative 9.81. In other words, if you're in a seatbelt and you get in a crash, your coffee cup would look to you, if you were watching your coffee cup during this crash, which you probably wouldn't do, but if there was a video inside the car, what it would look like happened to the coffee cup is that it would accelerate with a huge acceleration forward into the dashboard. And you know, I mean, that's sort of your experience. Is even if you just decelerate because you hit the brakes, anything you have sitting on your console or whatever goes flying forward.
Or even you.
Or you, if you're not in a seatbelt, yeah.
Even if you are in a seatbelt.
Yeah. If the seatbelt's tight enough, it's just your organs inside you that do that. Oh, yeah. Any questions about that one? Okay, that's all. See you Wednesday.